Hi guys. This is part 3 of the 5-axis CNC machine project. This time I am building the spindle unit. If you are interested in the design of this machine, please see the previous videos. The videos on this very unique design were more popular than I expected. I recommend watching those first if you haven't already. Let me explain the contents of this video. 1. What I added to the design. 2. Details of the spindle unit. 3. Creating the parts. 4. Assembly and adjustment. Here are the main contents. Designing a machine tool is hard work, but actually machining the parts and assembling them to a high accuracy is a completely different difficulty. Normally, when a machine is manufactured, design, machining, and assembly are done by different experts, but in the case of a self-made machine, everything is done by myself. Although this is a very difficult task, it has the advantage that the design can be done with machining and assembly in mind. Another important thing is that it is more enjoyable to do everything myself. Even if I fail, it's still enjoyable. Failure is the source of success. I believe that I can complete this machine because I have failed so many times before. I failed again this time too. This time, also, I have added something to the design. This machine's design is not yet complete. The layout of some parts has not been decided. One of them is the coolant tank and coolant pump. One of the ideas was to not add a pump, but in the end I decided to add one. First of all, where to install the pump and tank. After much consideration, I decided on this location. Let me explain why I decided on this location. The coolant nozzle is mounted on the spindle bracket. By placing the pump and tank in the carriage, the hoses can be shortened and the coolant system can be compacted. The disadvantage of this design is that the coolant tank is located in the back, making it difficult to check the amount of coolant in the tank. However, this can also be solved. I will explain it later. The pump used is this pump. This pump is called a peristaltic pump. The mechanism of the peristaltic pump is simple. As the rotor rotates, part of it tightens on the tubing, pushing the liquid inside the tubing forward. This pump is ideal for this machine for 4 reasons. 1. It allows fine flow control while maintaining a constant flow rate. Since this machine will be using the least amount of coolant, fine flow control is a necessity. 2. General pumps require the inside of the pump to be filled with liquid in order to suck in the liquid. But this type of pump can suck in air, so all you have to do is put the end of the hose into the coolant tank and it will suck up the coolant. So it is a very easy to handle pump. 3. The structure is simple, so it is unlikely to cause problems. And even if problems do occur, they are easy to deal with. 4. It can be perfectly controlled by Linux CNC because a stepping motor can be used. Furthermore, based on these advantages, I came up with a new idea. That is to manage the remaining coolant tank level on the Linux CNC control screen. In other words, since this pump has a fixed amount of coolant to push out per revolution, it should be possible to calculate how many revolutions it needs to make to empty the tank. By managing the number of rotations, it is possible to determine how much is left in the tank. For example, if the pump turns 100 revolutions, the tank will be empty. If the pump is running at 50 revolutions, then there is 50% coolant left. This idea sounds interesting, doesn't it? We can see the amount of coolant remaining on the control display. Furthermore, it should be possible to automatically stop the machine when the coolant level gets low. For example, the machine could automatically stop using M0 when the pump reaches 90 revolutions to prevent the coolant tank from emptying. I can't show you the part yet because it hasn't arrived yet, but when it does, I will test it to see if it works as I think it should. If you are interested in the results, I recommend you subscribe to this channel so you don't miss the video. That's all I have to add to the design. Now, I will explain the spindle in detail. This is the spindle. It is an AC motor with an outer diameter of 80 millimeters. This spindle is not recommended for steel machining, but since I mainly use a small diameter 3 millimeters end mill, I don't think it will be a problem. If there is a problem, I will consider it then. Many people have commented to me that this spindle may not be suitable for steel machining. I also wanted to use a spindle that is recommended for steel machining, but I gave up because the size of the machine would be too large to fit inside the soundproof box if I used a spindle larger than this. The collet is also small, an ER11. The maximum clamping size of the ER11 collet chuck is usually 7 millimeters. This size is sufficient for a 3 millimeters end mill. For the VFD, I chose 2.2 kilowatt inverter. What is a VFD? It stands for variable frequency drive. It is a device used to adjust the speed of a motor. It is especially used for AC motors. Simply put, VFD is like a speed controller for motors. The spindle is 1.5 kilowatt, but I decided to use a 2.2 kilowatt VFD. Using 2.2 kilowatt VFD with 1.5 kilowatt motors will provide more leeway under overload and peak load conditions, thus reducing stress on the motor and potentially extending the life of the motor as a result. I chose to use VFD with a little more leeway to use the spindle at higher performance. Next, let's talk about the linear guides. The linear guide I used before had one row of bearings per side and was small in size. The new linear guide is 15 millimeters and has 2 rows of bearings per side for a total of 4 rows. The stroke is designed to be 100 millimeters. The frame of the spindle unit is made entirely of aluminum. Why aluminum? Easy to machine, easy to obtain, lightweight, rust resistant, and other advantages. These are great advantages for building your own machine. They are especially great advantages for people like me who do not have sufficient machining facilities. The disadvantages are it is a bit expensive. Softer than steel. I decided to use aluminum because I thought the advantages outweighed the disadvantages. Let's start. Now that most of the parts are ready, let's temporarily assemble them. Bolt holes will be drilled after checking their positions while assembling. I am looking forward to the successful assembly. What the hell is this? There is not enough space to install the X-axis linear block. Oh my god. Somewhere is off by about 4 millimeters. I checked and found that the height of the side plate is too high. Why did I make this mistake? Maybe this is the cause. Normally I don't have this problem because I work with pure alcohol as a lubricant. However, when I made this part, it was Saturday morning and I was working with a cup of coffee. What's more, it was cheap instant coffee. There is no way that high accuracy machining can be done under such conditions. It was only natural that it would fail. It can't be helped that it failed. The part needs to be corrected. Next time, I will use enough lubricant to avoid failure. It's perfect. This time I was able to machine with more accuracy than an industrial laser machine. I should have done this from the beginning. The only problem is, I have a hangover tomorrow. Will I be able to go to work? I'd better go to bed early today. I am not sure what the next video will be. I am working on several videos at the same time, so I will release the completed ones first. What I plan to do now is continue with the spindle unit, testing carbon fiber and epoxy granite, and further upgrades to the CNC 1310. If you are interested in this project, I suggest you subscribe to my channel so you don't miss any videos. If you empathize with my project, why don't you become a member and support this channel? There are few benefits, but as long as you are a member, your name will appear at the end of the videos as a patron. In other words, you can be a part of this project. So, please look forward to the next video.